Hi, welcome to the Apple II Programming Channel. I'm your host, Dagan Brock. Today we're going to talk about something that I think is really interesting and really important for learning how to program, because if you want to get really good at something, whether it's writing or painting or any skill, it is extremely important to reference other people's work and learn from what other people are doing. And today we're going to do some of that through one of the most like I said, important methods I think that programmers have, which is disassembly, and we're also going to talk about reverse engineering. So disassembly is sort of the process of taking a program apart by reading the binary code and essentially reassembling some sort of source code out of that. And reverse engineering is just more generally figuring out how something works. So what we're actually going to talk about is this game called FutureShock 3D. I actually got a copy of this back in the day, somehow released as a Ware in the Wares scene, and I remember trying it and I couldn't quite get the controls to work well because I didn't have the FuturePad that it required, and so I kind of stored it away and didn't think about it. But it came up recently on Facebook. Somebody asked, hey, did the FuturePad ever really exist in the wild? So what was the FuturePad? It was basically kind of like this mouse pad, except it was some sort of electrostatic sort of capacitive device. Imagine a theremin, so as you moved your hand away, it could tell how far away your hand was, basically, and send that back to the computer. So the idea was, for this game, you'd move your character around the playfield with the mouse, and then with your sort of non-mouse hand, you would jump, or at least levitate or something, using this FuturePad over here. A bit wonky, but interesting idea. As it turns out, they actually did come out with the FuturePad at some point. I know it was at least spotted at some trade shows. A couple people have them. They say they're nothing to write home about as far as the overall construction, but it's interesting to know that they're out there. So I was able to get enough data to sort of reverse engineer how that FuturePad worked, and also get a little patch for this game so that we could try it out even if we don't have a FuturePad. So enough of me talking. Let's take a little closer look at the game, and then we'll get into sort of tearing down sort of not just the code, but trying to figure out how the FuturePad would have worked just by looking at the source code. Okay, let's go. The first thing I want to know to figure out how the FuturePad works is how it connects to the Apple IIgs. So I googled online and I only found 2 websites that even had pictures, and they weren't very detailed. But from what I could see, there was the pad with the window that kind of had the logo printed on it and a cable that ran to the computer. And at the end, it looked like a connector that was your standard D9 joystick connector. So it looks like it connects to the joystick ports, and that's our first clue. Now to take a look at the game, we booted up in an emulator, and I got this disk image off of the incredible website, What is the Apple IIgs, as seen on the bottom of your screen. It says it's by Nika Software, written by Jeff E. Johnson. Good job, Jeff. And published copyright by Nika Electronics, so clearly this was meant to be a pack-in game to promote the controller. So another clue, it tells us, warning, the FuturePad is not installed, so it can clearly detect that it's not connected to the system, even though we're using an emulator. But it's the same as it would be on a regular machine. So I'll start a new game, and I apologize. The game controls, I think, are a little bit sloppy. I'm not trying to beat up on the author, and that's without the ability to use the FuturePad to jump. But you use the mouse to move across the play field, and it basically feels kind of like a poor man's Marble Madness. So I'll let you watch me crash around a little bit and die, and then we'll get into tearing this thing apart. I want to cover one other thing real quickly before we dive into the super technical stuff, and that is disassembly. I'm not going to try and teach you how to become an expert at disassembly, but I want to give you enough of an overview so you can follow along with what I'm doing. So what is disassembly? Well, it's just like the word to disassemble means in English. You're taking something apart. And what we're taking apart in this case is an assembly language program. And the reason that we want to do that, and the reason you commonly would, is to understand it. You want to understand what the routines are doing, or maybe you want to see how the author did some cool trick. And our end goal for understanding it actually goes further, because a lot of times you just want to learn, but we want to actually understand it so that we can modify it and make the game FutureShock playable without the FuturePad. And of course, in the height of the Apple II days, a lot of people wanted to understand the tricks of other programmers, and particularly they wanted to understand the on-disk protection routines so that they could defeat those and crack the game and make playable copies. And those are two totally different goals, but they really rely on this core skill of disassembly quite a lot. Now, you might have heard before that computer programs are entirely made of ones and zeros. And that's true, but really you would almost never look at data that way. If you had a big stream of ones and zeros, it would be quite difficult to decode because it takes a lot of numbers to represent anything using binary digits or bits, because they just don't hold a lot of data. A single binary value just isn't that useful on its own because it can only be a 1 or a 0. So what we typically do is we put bits together. If you put 4 bits together, now all of a sudden you can represent up to 16 different values from 0 to 15. How does that work? So take a look at this table. And if you've ever studied programming, or especially assembly language programming, you've probably seen something like this and you're groaning and rolling your eyes about right now. But I don't want to teach everybody how to count in hexadecimal. I want to just make a quick point here. If you look at the column on the left, you have the binary numbering system, and the column on the right is the hexadecimal numbering system. So binary only has 0 and 1, hexadecimal has 16 values. It goes from 0 to F. So the reason we use hexadecimal is it lines up so nicely with the binary system. You can see if you look at the decimal column about halfway through, we have to start using 2 digits. And it doesn't really correlate to anything in the other 2 systems because it's not a power of 2. So if we were to go one higher, say the number 16, yeah, of course we'd have to add another digit. But again, you know, the binary and the hexadecimal lines up quite a lot better. And I'm making the point again that a hexadecimal digit can hold up to 4 bits of data, in other words, representing, you know, one of 16 values. And so commonly we'll put 2 of those together, 8 bits, to make up a byte. So a byte is 8 bits, and it's 2 hexadecimal digits, like it shows here, from 00 going all the way up to FF. And in our day-to-day decimal numbering system, that just means we're going from 0 up to 255. So there's 256 possible values in a byte. So now if we were to look at our program data, it might look something like this. And I kind of already know what you're saying, what you're thinking. Basically, that does not look that much easier than looking at a stream of ones and zeros. But trust me, it is. I can already tell, well, of course I know where this came from, that some of those instructions are load instructions because they start with A, and all the load instructions pretty much start with A. But that's okay. I don't expect you to memorize that and read it like the Matrix or something. We actually use a tool called a disassembler, and I'm going to use one in this video called the Flaming Bird disassembler. But one really cool thing about the Apple II is it has a built-in assembler and disassembler. So if you do call -151, you can get into what's called the monitor. And it's called the monitor because you can do things like monitor memory location. And you can say, hey, what's in memory addresses 300 to 30F? And it'll show, of course, nothing there right now, a bunch of zeros. If I put an exclamation point, I can go into the mini assembler, and now I can actually even write a little program. So we'll say, starting at that memory address 300, let's load into the accumulator. And the accumulator is just a register inside the CPU. So load A means load into the accumulator, and we're going to say the number 4. Now watch what happens when I hit enter. It translates that. It shows my load into A number 4 on the right, but on the left you'll see it has 300 A904. So it translated that instruction into the machine code, basically, that represents what I was trying to do. So let's continue our program. Let me give you another example. If I put load into a $4, we're going to load into the accumulator whatever is in the computer's memory at address location 4. And you can see it translated that differently. Instead of A9, it's A5. Now it still has 04 for the second argument, but the instruction itself is changed because it's doing a different type of operation. One is loading a real number, one is loading from a memory location. And one last thing that I want to show you on assembly so you can see how this works when it is assembled. What if instead of the loading from 4, I wanted to load from memory location 400? Now this is even different from the one above, even though we're loading from a memory address. But loading from memory address 4 is what's called a zero page or a direct page load. It's so low in memory that it uses one less byte to represent, so it's just 04. Whereas 400, we need 2 bytes to represent. But what I want to point out here is that if you look at the way it encoded it, it's AD0004. In other words, it swapped those two numbers around and put the 00 in front of the 4 for 400. And that's because memory locations in programs on this Apple II have the byte order reversed, where the least significant byte comes before the most significant byte. Alright, so that's like a little assembly language program. If I hit Control-C, I can go back, just hit Enter, go back to the monitor. And now I can look at that memory location again, and you can see it kind of looks like some of that same code that we saw up there, and you're probably thinking, okay, that's great. I get that you wrote some program and it put it in there like that, but I still don't know what that represents without you telling me. But I just want to show you that this is the built-in disassembler. If I type 300 and hit L to list it, now all of a sudden you can see it's disassembled my program starting at 300. And it shows my instructions that I typed in on the right, and you can see those hex bytes on the left. That's all. I just wanted to show you, you can assemble to get it into the computer, and there's a way to list it to get it disassembled back out. But this is a very basic disassembler, and we're going to use one with some more functionality. The one last thing I want to point out, if you look here, you can see that it's taken all of the zeros that were in memory after my program, and it's interpreted those as break instructions, break 00. On and on and on. The computer doesn't know what is your actual program code data and what is the data for, say, a picture or a song or a string of text. And that's where it uses some human skill to sort of suss out when you're in program land and when you're in data land, for lack of a better term. Okay, so hopefully that gives you a little kind of crazy intro to what you're trying to do when you're disassembling. You're trying to translate those numbers back into the right instructions, and the computer already knows what the possible right instructions are. So that's going to be our disassembly. Okay, now that we've taken a look at the game and I've talked a little bit about disassembly, let's get into this and start trying to figure out how this works. So let's take a look at the disk image itself. On top here, these are all system files and folders. Here's the only system16 file, which is the actual program. This FS folder has some playback demos and some resources. And this Toolkit one really sticks out because it's called Toolkit. And inside here we have some basic programs called readpad, readnorm, a binary file called fp.asm for assembly, I assume, a readme text, a readme basic. So let's check out that Toolkit stuff a little bit further. Go into basic, since there were some basic files that we might be able to run. So let's run the readme, which I'm assuming it actually is loading that readme off the file. And you can see this was the readme from the original creators, Nika Electronics. And it looks like this is basically saying that this is a driver really only intended for BASIC, and to contact them if you need some other driver. So let's take another look at that disk. Load let's see the read pad and see what that tells us. Okay, so there's really only two important lines here. Look at line 150, where they're basically loading that fp.asm file. So indeed that does seem to be some sort of driver. And then that apparently installs an ampersand command in BASIC for AppleSoft. You could kind of add on your own functions and use the ampersand as a call-in point. So if you look at line 250, that's exactly what they're doing. They're calling ampersand followed by a p equals and then a variable called I, which is an integer variable. Okay, so let's try this out, and we're just getting back -1. So that's another clue right there. We don't have anything plugged in and we're getting back -1. And just for the sake of looking at it, let's look at the other one, read norm. It looks like the only difference here is that this has a normalizing function and it uses ampersand n on line 250 instead of ampersand p. So let's take a look at this fp.asm file. Do a long catalog, and we'll just load it like they are using the dash command to load a binary file. So looking at fp.asm, we can see it's a binary file, it's very small, and it just loads into 300, so that's a very common place to do these little routines. And I'm going to switch back to 40 column to make it easier to see, and let's list out what we have for their program. Looking at this, it starts at 300 with real program data, which we already know because we were able to run the basic program which ran it, and it didn't crash. So the first thing would have to be a real instruction, and that's what it is. It loads the value 13 and hex and stores it somewhere, loads the value 3 in hex, stores that somewhere else, loads the value ff, stores that in 2 locations, and then exits out. So it doesn't seem to be doing a lot, but if you're familiar with AppleSoft Basic, you might recognize that location 3f6 and 3f7 is actually what's called the ampersand vector. So that's how you install those little ampersand add-ons. Let's go ahead and just go down a little bit further in the program, see if there's anything else particularly interesting. It looks like it does turn on some 2GS 65816 assembly because we see the clear carry and exchange carry down here. Okay, and here's an interesting one. It's loading from C063, which is related to the joystick. So it is using one of the joystick inputs. Let's just go ahead and Control C to get out of here and start to take a look at this in a full disassembler. We're going to use the Flaming Bird disassembler by Phoenix Corporation, written by Ferox, as it says here. Now this is a full-featured Apple IIgs disassembler that can do regular Apple II binary files, ProDOS 8 files, System16 files, and it has a typical sort of Apple II interface. We've got a command line. You can pull up the help, and there's a manual which I've translated the main manual from French into English, which is all available at the Brutal Deluxe website. But I'm just going to kind of take you on a quick tour and do a somewhat live disassembly, although I've already done this one once before. So the first thing is going to be basically loading that same fp.asm file. So we do that with the load command, pretty straightforward. And it already read the aux type and put an org statement to say that this disassembly starts at 300, which is correct. And immediately you'll see something is off here because our first load instruction was loading the number 13 before, I remember that, and this one is loading a 2-byte value, 8D13, and that's because this thinks that we are in full 2GS mode right now. So we're going to go ahead and first let's just give our program a label at the starting point, and then we'll fix that. So that just assigns a label to the memory location 300 in our program. So now we can refer to that by name, and it will also track that name as we're doing our disassembly. So we're going to add a couple more labels as we do this. Now we can tell the disassembler that we want to set the M and X registers, which represent the accumulator and the X and Y index registers inside the processor. at that label main, both to emulation mode. So set them, sorry, I need a percent here, it's a binary value. So we want to set those to 8-bit mode. Now all of a sudden it looks different. And you'll notice something else. It loads 13, but it also recognizes that we are writing something to the ampersand vector, and it's automatically put in that well-known location with a label for us that's meaningful. Alright, taking a quick look at what's storing in the ampersand vector, it's really storing the value 313. First it stores the value 13, and then after that 03, and remember the memory addresses are swapped. This tells us that the entry point for the ampersand commands is at 313, so let's go ahead and put a label there. We'll call that entry. And what is entry doing? Well, it loads a couple of values, does a comparison, and eventually it does a jump to subroutine at 35B. So that's down here. Let's check out 35B. And that does its own jump to subroutine at 34E. Let's look at that. Okay, so this one's interesting. It basically turns on the full native mode of the 65816 registers, and it sets us to bank 0. So let's go ahead. So let's put a label on this routine that kind of describes that. 34E, we'll call it bank 0, 16-bit. So looking at 35B, first thing it did was jump to that routine that set it to bank 0 and full 16-bit mode. Now that we're back, we're actually turning the accumulator back into 8-bit mode with this set processor 20 command. Then we're turning off interrupts so that we can do presumably some sort of read function for this FuturePad. And then we load a value 2710 into X, and we don't know why. All of a sudden starts to get into a loop where it is reading that button 2 value, and again the disassembler has automatically put that in. And button 2 is not often used because most joysticks don't have a button 2. They have a button 0 and a button 1, but it is wired up. So let's go ahead and call this 35B. This looks like it is the reading routine. So we call this one readPad. And now it's time to kind of figure out a little bit more about how it's working. You can see that after it loads that magic number 2710, it decrements it using the decrement X command, and then it branches if it gets beyond 0, that is if it wraps around to -1. So that kind of ties up to our second clue there. When we ran the basic program, we got a -1, and we don't have a FuturePad, so looks like that might be kind of how it bombs out. Let's go ahead and look a little further. You can see it checks the button 2 value and does branch if minus. So if it's, let's see, what would that be? Branch if minus, that means the button is pressed, I believe. So let's do this. Let's go ahead and assign a label to that loop where it just keeps reading this button state over and over and over, starting at 364, and it looks like sort of a subroutine, so I'm just going to use an underscore just to kind of keep it separate in my head. So if it gets past that and they either, I guess, push the button before that times out, then it goes to this next loop where it does another pretty much the same thing. It just keeps decrementing X again, and as long as it doesn't bomb out, it looks for the button this time to be branch if plus. So we'll call this 36C loop 2. Okay, now they clear X and we are counting up and waiting for we're doing another loop, but this time we're doing branch if minus again, so we're waiting for the button state to change one more time. If it does, then we store that value in 2 locations down here, 3B7 and 3B9. So let's first label that loop. Actually, I think I have loop 3, which starts at, let's say 377. And it looks like this other location, 37D, that where they bomb out to if they underflow, just sets the processor flag back stores the result. So that does look like sort of an exit. We'll go ahead and put that on there. That's where it stores your result and exits out. So if your result is that you timed out, it would store FFFF, which is basically -1. Alright, now you can see that's, and that's basically it. And then it returns down here. We have another routine after that return that seems to read the pad. And it looks like this one basically reads it and compares it to a previous value and tries to make sure that it kind of clamps down on the maximum amount of change there. So this must be the read normalized. So we'll go ahead and just label it as such. Read pad, or we'll just call it read p norm. And what else do we have? There were those locations that they stored the data in, 3B7 and 3B9. So let's go ahead and give those names to 3B7. I don't really know what it is. It's, oh, and 3B. Is there another one? Yeah, and 3B5 in this routine. So 3B5, we'll call that data 0. 3B7, we'll call data 1. And 3B9, and 3B9 we'll call data 2. So now you can really start to see a lot of the program being defined and having labels, and even if you don't understand assembly, trust me, this is actually getting a lot closer to the answers. We have an idea here about how it reads it, and it basically looks like it's checking for the button states to toggle. The way it's doing it is probably way too fast for a human. At this point, I think we have all that we need from the basic driver for the FuturePad to understand how to actually read it. The rest of the code I did disassemble, and I put it on a GitHub gist with relatively complete comments, but as you can see, a lot of it has to do with just how it decodes, whether you put in a P or an N. And then when we get down to the actual read routines, it's really just this small part right here where, again, like I said, we check in these 3 loops, first for the button to be down, and then up, and then down again. And on that last down phase, we actually start from 0 and count up to determine how long the cycle was. So why would they do that? Let's take a look at an oscilloscope, and we can imagine that this line here is actually button presses, or essentially toggles of that button 2 line for the joystick. So again, what they're doing is they're looking for first the button to hit the down state, and they're doing that basically to detect that it even is in there. The device should be flapping back and forth. Now it may not be symmetrical like this, I don't know. The up state may actually be very short since it is not that important. So they wait for a down state to happen, and then after that they wait for an up state to happen, and then they wait for one more down state, and this one they count. And that's really basically it. Again, as your hand moves up and down on the pad, you just expect the wave to move something like this. Now that we know a bit more about how the FuturePad read routines work, we need to actually find that in the game code and patch that with some other code, and I'm going to try and patch it with something that reads a joystick. So I'm just opening a hex editor, and I'm going to open the disk image and not even take the files out of it. I'm just going to try and do this patch on the image. So the first thing we want to look for is that C063 value. But remember, that's a memory location, so the bytes will be swapped. So we're actually going to be looking for 63C0. So here's our first hit. And this is interesting because it uses AF in front of the 63, which, remember I said A is load instruction. So let's see which one that is. And that is actually right here, AF, which is a load long, and it takes a 24-bit address. So what does that mean? It means we're not actually loading C063, we're loading E0. So there's a bank system in the 65816 which is used on the Apple IIgs. So we're loading from bank E0 C063, so the full address is E0 C063. That is good. That means we have found the right code for reading that button 2, most likely. So let's take a look at where this starts. I think it's going to be right here. That looks like the first valid opcode, though it could be down there. And see how long this is. I'm looking for some sort of return, which would be 60 for a return from subroutine, or 6B. That's it, and that looks like another little segment header right there. So that's the code, presumably for our read pad, but we can kind of verify that in a pretty crazy way, quick and dirty. We can load up our emulator, and I'm just going to take some of this out of here and use a paste function to put those bytes into memory, and let's go ahead and do a quick disassembly. So sure enough, that looks very much like Apple IIgs assembly code. You can see our LDA E0C063. So this is definitely where I want to be. Let's see what else it is doing. So we stopped right here. I don't know if I can paste in the entire amount at once. Let's do a couple more. Starting at 320 now. Oops, 320 list. Oh, actually I missed an earlier return, so that must be the two routines put together, the normalized and the regular routine. So yeah, this code looks nearly identical to the basic driver that we were disassembling earlier. The big difference here being that since it's running from anywhere in the Apple IIgs's memory, it does a long load from bank E0 to read that button 2 line. Other than that, it transfers that final X value to A and stores it in memory location 0002. So I think as long as I do the same thing, return the value in A and store it in that memory location, and as long as my code is smaller than what is already there on disk, I should be able to just stick it right in there on the disk and have a working patch. I wrote this patch, which is really simple. I use a tool call here. I stop interrupts. I don't know if the tool call would handle that for me or not, because this is a special tool call that says I want to call one of the Apple II firmware routines from an earlier model, and those typically require that you kind of turn off a lot of the 2GS stuff to get in there. And the routine I'm going to call is this paddle routine, and with the value 1, so I want to read the y-axis, and then we take that result, which comes back in y, and transfer it to the accumulator, and then I'm going to multiply it by 2, because when I originally tried this patch I just did a low amount and I could only jump a little bit. I don't really know the full range of the FuturePad return values. We did work out some of the timing in a Twitter conversation between another programmer and myself, but I wasn't that concerned with getting it perfect. I just wanted something to kind of play around with. Again, I store that value in 2, and it turns out that's really all I needed to do, and return it in the accumulator, which I believe it's actually using the accumulator value. So to get my patch on there, the first thing I need to do is assemble it, and I'm using Merlin, specifically Merlin 32 by Brutal Deluxe, which is really great because it runs on modern operating systems and is very, very compatible with standard Merlin source code. So then I basically just dumped out my patch output and pasted it in back in Hexfiend. Go back up to the beginning of where our routine was, starting right here, and paste that first line. And yes, I really did it this haphazardly, copy pasta. Go ahead and get all, don't want to miss a single byte. This is important code in here. 1, 2, 3. And it doesn't even matter that we run into other junk after this RTL, return long. So from there, I can just save my disk image, and we should be able to run it. Okay, so now I'm booting up that same image that we saw at the beginning. And it even still has my folders open the way I had them, so I hope it made the changes correctly. Now I'm going to launch that same program. I'm just using a modern gamepad hooked up to my computer running this emulator. It basically acts like a normal joystick. Now the first thing you'll notice is it didn't time out on that read routine because I've already replaced apparently the global place where it reads, and if it got a -1 from there, which my routine can't even do, it would have timed out. So I can do a new game now, and let's see if I can jump. I'm going to flick the axis so it jumps. If I hold down, it actually goes up, and if I hold up, it goes down. So in a way I have the axis inverted, but this is already a lot better. So pretty cool. I don't know that I would play it, maybe if I fixed the axis, but alright, I don't really know what the point is. I think you're supposed to get the keys. But anyway, I succeeded in my goal of at least getting some way to play the game without having the FuturePad controller and having a little patch to do it. Okay, so that's it for me for this time. That may seem like a kind of incomplete patch because it's I had the joystick axis inverted and some other things like that. And it is. I considered doing a full patch because I thought that would be good for the community and preservation to be able to play it. But I mostly got out of the project what I wanted to, which was just to learn how the FuturePad worked and to see if I could do a patch. Still, I thought it was worth doing it, and I was kind of asking a friend of mine, Antoine Vigneault of Brutal Deluxe, if he would consider doing one, and he was very kind and said, no, you know, you take it to the end, you finish it. And at some point, a day or two later, I got sick, I had a bad cold, and I think he finally took pity on me and decided to do a proper patch. So now you can go to what is the Apple IIgs website and get a patch version of this game if you want to try it out for yourself. And Antoine is extremely good at disassembling software, and he has been so kind as to include a full disassembly of the game as he has it on that disk image. So definitely check that out. Thanks so much, Antoine. That was great work as usual. If you're really interested in disassembly and you're looking for resources, I think one of the best modern contemporary resources that we have are the crack write-ups by 4am. So check out 4am's Twitter and go check out his crack write-ups at the Internet Archive. Just great stuff, chock full of information, and probably in a better way than I do, he takes you through the process and the thought process of doing that sort of disassembly, and his is of course focused on defeating on-disk protection. So thanks for all those guys and their inspiration, and I have to thank my Patreon, Ken Gagney. Without him, I would not have done this video. This video took probably 10 times as long as it took me to do that patch in the real world, which maybe took a bit of an afternoon and a bit of an evening, and this has taken me about 2 weeks to kind of put together. But that's okay. We're keeping it going, and I will have more videos a little bit more focused on the building of software in the near future. But hey, sometimes you got to take it apart to learn how to build it. All right, have a good time, everybody. Bye-bye.